Yeah. Okay. So let us begin. As I was telling, I will just repeat most of the things which are yesterday. There may be a few points which I may mention, which is extra. So the first thing is the concept of mean molecular weight. And let me just first discuss the basic philosophy of it. Okay. Now, an example to begin with is molecular weight of water. So what is it equal to? So basically it is, when I say molecular weight of water, it is mass of water molecule divided by mass of a nucleon or a hydrogen atom. Okay, fine. And this comes out to be 18. Okay. So now, so now what you do is you generalize this. So now you generalize it. Mass of any particle, sorry, molecular weight of any particle is given by mass of that particle divided by mass of nucleon or hydrogen atom. We will assume that the masses are roughly the same, basically because the electron mass is supposed to be negligible with as compared to the proton. Okay, so it means that the molecular weight highlight it. I will just use a different color. So molecular weight of a particle is equal to mass of that particle in units of nucleon or hydrogen atom mass. So this is the generalization of that. So which means that for saying molecular weight, it need not be a molecule. It can be any particle. Okay. Now, in the astrophysical context, we will assume that mass of proton is equal to mass of neutron is equal to mass of hydrogen atom, and which is roughly 1/4 times mass of the helium atom. Okay. And this this also assumes mass of the electron is much less than the mass of the proton, and hence Me is neglected as compared to MP. So this is the assumption, and this is because we know that mass of electron is about 1/2000 times the mass of the proton. So this is the approximation in which we will be working. Okay, so far so good. Divya, you just joined. Now you can just see what I have written. I hope it is clear. Okay. Right. So now let's go to the next thing. Is what I call the mean molecular weight. Okay. And so let us first consider for a pure gas. Okay, for a pure gas. And for a pure gas, we already discussed in the first lecture, and I also gave some problem in which we showed that since the matter is ionized, the fundamental entities, the particles, are protons and electrons, whose size is much smaller than the size of the atom, and hence the total volume occupied by individual particles is much smaller than the total volume occupied by the system of gas. Further, we also had this calculation in which we calculated the kinetic energy of these free particles and the potential, in which we calculated the pressure of the central pressure and the electrostatic force inside the atom, and we showed that the atom is crushed and cannot exist as neutral, and so the fundamental particles are protons and electrons whose volume is much less, and further the temperatures at the center are large enough that the interparticle potential energy is negligible, which means particles interact only when they are scattering. So it means that all the conditions of an ideal gas are satisfied by these ionized matter. Is that clear?
Yes, sir.
Okay, good. Okay, fine. Now, so this implies that we can say that the pressure is equal to nkt, and so this is pressure, and this is the number density. Here I'm talking about a pure gas, okay? And so now I can write this as pressure is equal to rho density by mass of the particle into kT. And this can be written as density into kT divided by the atomic weight of the particle times mass of the proton. Is that okay?
Yeah, okay, sir.
Okay.
Yes.
And so, okay, so I will, okay, so I will write, so what I do is okay, so for any particle, if suppose P is equal to sum 1 by A times rho kT by MP, then this is what is identified as the molecular weight. Okay, sorry, not molecular weight. A is the molecular weight. Okay, for example, if it is hydrogen, it will just be the mass of the proton, so it will be 1. But now we can generalize it. How do we generalize it? We can generalize it by saying for a mixture, of gases, I know that okay, for a mixture of gases, I know that total pressure, rather I should say the following. Okay, I'll just repeat this. Suppose I take the total pressure and write it as total density into kT divided by some quantity mu into MP. Then this quantity mu is in the same status as A. For a pure gas, I call it molecular weight. So this is something like the mean molecular weight of the whole thing, and I call this mu as the mean molecular weight. Okay, we'll get the expression for that. But do you understand this? So what is being said is, so okay, so let me put it this way. Alternatively, for pure gas, the molecular weight A can be defined as rho kT by P into MP. This is for pure gas. Now I generalize it by saying that the total density multiplied by kT divided by total pressure into MP is defined as mu, the mean molecular weight. Is the definition clear? Hey, I already wrote in that thing that please respond. So this is the mean molecular weight. Okay. So now there is an important assumption here. The important assumption here is that for all the constituents of the mixture, I have taken a common temperature T.
Sir?
Yes?
Sir?
Yes?
Sir, can you please repeat the definition of
mean molecular weight?
mean molecular weight.
No, it is just
Mean molecular weight.
Yeah. So you understand the definition of molecular weight? I've just used this.
Yes, sir.
Okay, so you just use this thing. This thing. Okay. And now what I do is I generalize it. Here the density was for the pure gas. I now take the total density of the mixture. And I take the total pressure of the mixture. And substitute it for this, and I calculate such a quantity. Okay, this is the generalization. This is the generalization here. And I calculate this quantity. And this I define as a mean molecular weight. So in the special case, when the mixture is a pure gas, mu will turn out to be A. Is this clear, Kausalya?
Yes, sir.
Okay, I'm just generalizing. See, if it was pure, I know this is a definition. Now I'll say even for any mixture, I will call this. So it is as if, okay, so let me put it this way. If I have, okay, so I can alternatively put it this way. Mean molecular weight is equal to of mixture is the molecular weight of that pure gas whose density is equal to density of mixture and pressure is equal to pressure of mixture and is at the same temperature as the mixture. Okay, so this is what is the definition from here. Is this clear?
Yes.
Okay, good. Okay, fine. Now, okay. So now let me give some examples. Okay. I'll give an example of okay. Calculate mean molecular weight of a mixture consisting of just a minute. Density. Okay. So calculate the mean molecular weight of a mixture consisting of 75% hydrogen and 25% helium by weight. Okay, so this is the question. So what do I do? The total pressure is equal to pressure of hydrogen plus pressure of helium, which is equal to density of hydrogen divided by atomic weight of hydrogen, which is 1, into MP into KT plus rho helium divided by atomic weight of helium, MP times KT. And so this is equal to rho H, okay? Let me just write it down here. So we know that AH is equal to 1, AHE is equal to 4. And so I have, so this is equal to rho H by MP plus rho HE by 4 MP KT, which is equal to, now, so what is, see, H equal to 75% by weight implies rho H is equal to 0.75 rho total. Similarly, HE is equal to 25% by weight. This implies rho of HE is equal to 0.25 times rho T. This and this gives the total pressure is equal to 0.75 plus 0.25 by 4 times rho total KT by MP. And so I can write this as P total is equal to rho total by 1 divided by, okay, so let me just simplify it here itself. Okay. Okay, so this is equal to, this will be what? This will be 0.7, this is 3.25. So this will be 3.25 by 4 times rho total KT by MP. And so this is equal to rho total KT by 4 by 3.25 times MP. And if I compare this with this, I get mu is equal to 4 by 3.25, which is whatever, I mean, some number. Okay, I think probably it's 1.23. Yeah, so the mean molecular weight of the mixture is 1.23. So do you understand the calculation?
Yes.
Okay, good. Okay. Right. So now, so let me now take some more example, which is now in the astrophysical context. Okay. More examples for mean molecular weight astrophysical context. Okay. Now, so let me consider the case of a fully ionized hydrogen. Now, if it is a fully ionized hydrogen, is it a pure gas or a mixed gas?
It's a mixed gas, right? You have different particles.
Yes, since it is ionized, the fundamental particles are electrons and protons. So it is not a same kind of particle everywhere. So it's a mixture.
Sir, but if you take it like that, then I think the last class you had mentioned an approximation where you consider the mass of the electron to be negligible.
Yeah.
And so then we can consider it to be homogeneous, right? If it's going to be just the mass of
I will come to it. The reason is the contribution to mass and density comes only from the proton. Mass electron is negligible. Yeah. But the pressure depends on the number density. So electron will equally contribute to number density, to pressure. Because the number density of electron, that's why it's a mixture. Okay, good. Okay. So the total density is equal to rho h. Now it is fully ionized, and this implies no neutral hydrogen. Hence, mixture of proton gas and electron gas. Okay. And now, so suppose the total number density of original, okay. Original number density of hydrogen is NH0, which is equal to rho h by MP. Okay. And pressure, but after ionization, we have the total pressure P is equal to P of electron plus pressure of proton. Now this is equal to what? It is the number density of electron times kT plus number density of proton times kT. Okay, is equal to number density of electron plus number density of proton plus kT. Okay. Now, since one hydrogen atom gives one electron and one proton, this implies that Ne is always equal to Np. And therefore, P is equal to twice Np kT. Okay, and Np is nothing else but twice original number density of hydrogen atoms times kT. Now, what is okay. And so this is equal to rho h kT twice by Mp, which is equal to rho h kT by half Mp, implies mu equal to half is a mean molecular weight. Is it clear?
Yes, sir. Clear.
Yeah. So
Yeah,
basically one can understand it in this way. See, since we are neglecting the mass of the electron, we are basically finding the average of 0 and 1, which is half. See, the atomic weight of a proton is 1. Electron, I'm taking 0. So the mean is half because they are in equal number. So this is a simple way of looking at it. Okay. Now we will come to a bit more complicated example, which is mean molecular weight of partially ionized hydrogen. Okay. And so I will say the following, that suppose NH initial is equal to initial number density of hydrogen atoms. Yeah. Hello. So this is the initial hydrogen atoms before ionization. Now let degree of ionization is equal to X, which implies X into NHI equal to number of ionized hydrogen, which implies number density of electrons Ne is equal to XNHI, number density of protons is equal to Np is equal to X into NHI, they are in equal number, and number density of neutral H atoms is equal to 1 minus X times NHI. Is this clear?
Yeah, yes, sir.
Okay, because this is so it is the fraction of hydrogen atoms ionized. Okay, fine. Right. Now, the total pressure P will be equal to the pressure due to electrons plus pressure due to protons plus pressure due to the neutral hydrogen atoms. And this will be equal to Ne plus Np plus NH times kT, because the temperature is common. And so this will be equal to X NHI plus X NHI plus 1 minus X NHI into KT, which is equal to, if you just solve it out, you will get this is equal to 1 plus X into NHI into KT. And that is equal to 1 plus X. Now, by ionization, the density does not change, the mass density. So this is basically rho divided by MP KT. And so this is equal to, so P is equal to rho KT divided by 1 by X plus 1, or just to be consistent, times MP, implies the mean molecular weight is 1 by 1 plus X. Now we can check X equal to 0, mu equal to 1, matches with neutral hydrogen. X equal to 1, then mu equal to half, we calculated, matches with fully ionized hydrogen. Are you with me?
Yes, sir.
Okay. So if you have a partially ionized thing, this is what happens. Now I will, before I go over further to another topic, virial theorem, I will just consider one example which is a bit more complicated. Okay. And that is, mean molecular weight of a mix of okay, fully ionized mixture of hydrogen, helium, and higher elements. And at this point, there's an important terminology which you should remember, which is in astrophysics terminology, all elements other than hydrogen and helium are called metals. It's a general terminology. So in this terminology, oxygen is also referred to as metal. Okay. Basically, metals means elements higher than hydrogen and helium. Is this clear? It does not mean in the same situations as metals in chemistry. We are not talking about its chemical properties. By metals, we just mean okay. By metals, we mean that just 1 minute. By metals, we just mean heavier elements. Okay. And so that's why we say, okay, so we say for heavier elements as metals. Okay. Now I want to calculate the, okay, the question is, uh, calculate mean molecular weight of a fully ionized mixture of gas consisting of uh, a fraction x bar, a fraction x bar of hydrogen, y bar of helium, and z bar of metals by weight. Okay. So, I mean, it's very important because, when you say fraction, you can ask by weight or by number. It is by weight I am saying. Is it okay?
Yeah.
Okay. So now clearly this implies that z bar is equal to 1 minus x bar minus y bar because they are all fractions. Okay. And they are fully ionized. Ionized. And that implies that number of, okay, so any H equal to number density of electrons coming from hydrogen ionization is equal to uh, number density of hydrogen. Okay, because it's the same, these two. Now, number density of electrons from helium is equal to twice number density of helium nucleus. You understand this? Because each helium nucleus will 2. Now, number density of electrons from metals will be equal to the atomic number times the number density of the metals. Okay, because atomic number is the number of electrons it gives. And hence, number density of electrons is equal to number density of hydrogen plus twice the number density of helium plus Z times the number density of metals. Is that okay?
Yeah.
And now, and so this is equal to rho H by MP plus twice rho HE by 4 MP, or I will just write one more step in between. Plus Z times rho M divided by mass of the metals. And this is equal to, rho is equal to, what is rho H? Rho H is X bar times the total rho, because it's a hydrogen fraction, divided by MP plus Y bar, okay, plus twice Y bar rho HE by, sorry, rho bar H, because this is rho H, by 4 times MP plus Z times Z bar rho divided by the atomic weight of the metals times MP. And this is equal to X bar plus 2 plus half Y bar plus plus Z by A, Z bar, the whole thing times rho by MP. Okay. Now, note that Z bar is equal to 1 minus X bar minus Y bar. Also, for heavier elements, we have Z by A is about half. Right? Because the number of protons are about half the total number of nucleons. This implies, okay, so all these imply number density just 1 minute. Yes, so this implies that number density of electrons is equal to X bar plus half Y bar plus 1 minus X bar minus Y bar by 2 times rho by MP. Okay. And now, so total pressure is equal to pressure of electron plus pressure of helium, hydrogen, plus pressure of helium plus pressure of metals. And so this will be equal to any plus NH plus NHE plus NM times KT. And so this is equal to what? I have got X bar plus half Y bar plus half minus X bar by 2 minus Y bar by 2. Okay, let us see. Yeah. Okay. This is from Ne plus NH, which is, I just messed it up a bit. No, just a minute. I'll just do the following. I'll just write on one more step in between. Now, NH is equal to X bar rho by MP. NHE is equal to Y bar by 4 rho by MP. And NM is equal to 1 minus X bar minus Y bar. Just 1 minute. I'm doing something wrong. No, it's okay. This divided by rho times atomic weight times MP. All right. Atomic weight times. I should get. Oh, sorry. Okay. Okay. I'm sorry. I'll just backtrack a bit.
Okay,
Okay.
sure.
I will backtrack a bit. Okay, let me just remove this. I'm just making the algebra complicated. Okay. So this is my NE. Okay. And then I have NH is equal to X bar rho by MP. NHE is equal to Y bar rho by 4 MP. And N metal is equal to Z bar rho by Z bar rho by AMP. Okay. And so P is equal to PE plus PH plus PHE plus P metal, which is equal to NE plus NH plus NHE plus N metal times KT. And from here, this is equal to, we'll just substitute it from here. I will have X bar plus half Y bar plus, okay, plus Z by A Z bar plus X bar plus 1 by 4 Y bar plus Z bar by A into KT. And so this is equal to 2X bar plus 3 by 4 Y bar plus 1 plus Z by A times Z bar. Yes. KT. Is this okay?
Yeah, that's fine.
No. Huh.
Okay.
Yeah. Right? This rho by MP will come out. Okay. And now this, I can now there are two things. One is for metals, I assume Z is much larger than 1. Okay. And Z by A is approximately half. Okay. Now here is an important.
Can you?
Huh?
How is the Z by half?
Oh, that is because in all the higher metals, the number of electrons will be, number of protons will be roughly equal to the number of neutrons.
Okay.
Okay, but I will
Okay.
tell you,
Yeah.
no, here there's an important thing. But you know that for lithium it is not.
Yes.
Okay, the reason why it works it's because in stars, Z bar is actually much smaller than 1. Hence, negligible error is there. See, even if this quantity is considerably wrong, the weightage given to this is very small because Z bar is something like at best 0.1. Not 0.1, 0.01. Okay. Anirudh, is it clear? Anirudh? Hello?
Sir, you're audible, sir.
I think Anirudh has disappeared. Yeah, okay. So this is negligible. You understand this now, why it is this approximation works?
Yeah.
Okay. Yeah. Okay. So let me just rearrange it a bit so as to make everything into one page. ये क्या हो गया? Oh. Okay. And now what I say, so okay. So now if I substitute, okay, so from here, I will get 2x bar by 3 by 4 y bar plus 1 plus z by a 1 minus x bar minus y bar. Rho kt by mp. And so if I use this, I mean, if I use yeah, just if I use this with this, I can actually calculate, and I don't remember the number which will be there. I've got it here. I will get it as P is equal to what is this? Wait. I've done what's some mistake which I have done yesterday's thing. Okay. P will be equal to, you can actually calculate it. I mean, so let's just do that quickly. So I will have 2x bar plus 1 by 2 x bar from here. Sorry. Rather, let me put it this way. 2x bar plus 3 by 2 y bar plus half minus x bar by 2 minus y bar by 2. Okay. And so this will be equal to 3x bar by 2 plus y bar by 4. Isn't it? I mean, this, and this will be plus half. Okay. And so I will, so now I can take this LCM, SHLCM, everything. And so I can say that the 1 by mean molecular weight will be equal to 3x bar by 2 plus y bar by 4 plus half. Is this clear?
Yes, sir.
Okay. What about others?
Yes, Sesh.
Okay, good. Okay, fine. So I will just remove this. So I will have mu is equal to 1 divided by 3x bar by 2 by y bar by 4 plus 1 by 2. Just calculate this and make sure it is correct. So this is the kind of a realistic example in astrophysics where we mean molecular weight is calculated. Okay, so this will end the mean molecular weight thing, and this was exactly, I'm exactly on time as I was yesterday. Is this fine?
Yeah, sure.
Okay. So now I will go to yesterday. What I did was virial theorem.
Yeah.
Okay. So yeah. Okay, I'll just take a break for 5 minutes. Generally, grab a cup of coffee from ground floor and come.
Yeah.
Hi, sorry, I got late. Yeah. I mean, the coffee was not yet prepared, so it had to wait. Shall we start?
Yes, sir.
Yeah. Okay. So the next topic is, you see, all these things like mean molecular weight, these are all the weaponry I have collected so that we can use it as and when we require it. I think Kausalya has somehow left. Okay. 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 So next topic is the virial theorem. Now, what does the virial theorem say? First of all, let us consider a set of particles which interact with each other by a potential which is of the form xi of this kind. Okay, so which I call Raj. This is the potential. Potential between I and J particle. Okay. Let me not call it as, I will call this as phi because of a specific reason. And then I say that the potential experienced by I, which is V of xi, is equal to summation over all j not equal to I, phi I minus phi j, this one. Okay, so this is the total potential of the system. What I need to do is to calculate half summation mi xi dot xi summation over I. And this, I think this is what is called the virial. I will sort of confirm it, but this is called the virial. And the virial theorem states in equilibrium, which is called the virial equilibrium, d2 by dt square of half summation mi xi dot xi is equal to 0. So in some sense, it is the fact that it is the first time derivative of this object does not vary with time. That's what it means. Okay, so in other words, that is d by dt of half summation mi xi dot xi constant with time. And that is the kind of thing equilibrium, because in equilibrium it has reached a steady state. It will not, and this is something which is there. Okay. Okay. So now let us calculate this object. d by dt of, okay, I have actually calculated this. I can, okay, so let me do the following. Okay, so let me just say this. Yeah. Okay, so now I have d by dt of half summation xi mi xi dot xi is equal to summation I mi xi dot xi dot. Basically, a 2 will come out, cancel with this 2. Is this okay?
Yeah, yes, sir.
Okay. And then now I have d2 by dt square of half I mi xi dot xi is equal to d by dt of I mi xi dot xi dot, which is equal to summation mi xi dot xi dot I plus summation mi xi dot xi double dot. This quantity is what? This is 2 into the total kinetic energy. It is twice the half mi summation. Is this clear?
Yes, sir.
Hmm? And now let us consider this portion. Okay, so let me call it, let me call it the summation as S. Now S, what is Xi? Xi will be equal to, Xi double dot will be equal to minus gradient I times V. And so this will be equal to minus gradient of, we had this thing about, okay, summation j not equal to I phi xi minus xj okay, this is what it is. Now we specialize to the case when phi of xi minus xj is j is equal to alpha times xi minus xj to the power n. Okay. For example, if it is gravity, n will be minus 1. If it is simple harmonic oscillator, n will be 2.
Okay.
Okay. And so now I can now use this thing here, and there is actually okay. So if I use this here, now this will be, okay. So now I take the gradient of this. Now the gradient of I of phi will be equal to, I will write this as gradient of, I will write it in a slightly different way. I'll put it as alpha xi minus xj dot xi minus xj n by 2. Are you with me?
Yeah.
Okay. And so this will be equal to gradient. Okay, so this will be equal to alpha times n by 2 times xi minus xj dot xi minus xj n by 2 into twice xi into twice xi. Just a minute. Twice xi minus xj. All right. And this is equal to n alpha xi minus xj n by 2 into xi minus xj. Okay.
Yeah.
Now, what I have in this term here, the S is equal to summation I mi xi into del I with a minus sign because the minus gradient phi. So which is equal to minus summation mi n alpha xi dot xi minus xj times xi minus xj dot xi minus xj n by 2. Okay. Yes. So this is summation over G. Right? Oh, this
What
is
about
summation ing.
Yeah.
Okay. And now we need to invoke the following. This you can just do the details. You can invoke the following that I and J can be interchanged and potential between I and J I and J should be counted only once.
Symmetric.
Yeah. I mean, it's anti-symmetric, so you'll have to do just try out some jugad. I mean, you'll have to rename I and J and use these things and give the result, okay? Should be counted only once.
Divided by 2 then.
Yeah. So there will be a divided by 2 when that thing is coming. And if you, so what will happen is you will have S to be of the form n times summation alpha xi minus xj xi minus xj n by 2 I, which is equal to n times v. Okay, so sorry. So n times this one. N times, what was it? Yeah, it will be n times the summation of I vi, the total potential energy, which is equal to n times the total potential energy. Okay, this is an involved thing which I will please solve. Okay. And so we have d2 by dt square half summation mi xi dot xi equal to 0 implies twice the kinetic energy minus n times the potential energy equal to 0. And that is because there's a minus sign here. I mean, I think, yeah. Yeah, you can just work it out. I mean, no, like, it will come out. This is what will come out.
Okay.
Okay, please solve and confirm. And this is the virial theorem. Okay. Now, special cases. I'm just seeing if I can accommodate. Okay. Yeah. Okay. And now I will give some examples of virial theorem. Okay. Any question till now? Anybody?
So what do we conclude from Weyl theorem?
Okay. Good question. So it means the following. You see, if suppose this quantity does not change with time, what it actually means is that the system is, somebody is. Kausalya, you've been waiting for a long time, is it? Kausalya? Kausalya? Kausalya, you've been waiting for a long time, is it? Okay, fine. Okay, so what it says is this, if suppose this thing does not change with time.
Yeah.
Okay. Pardon? What happened? Okay, so what it means that the system does not change its shape, or it is not contracting or expanding. It has some kind of a steady state it has reached. For example, you take a star. Individual molecules may be roaming around in the star, but overall the star size and shape remains constant in time. Hello?
Yeah, yes, sir. But that will be an ideal case, right, sir?
Oh, no. So, yeah. So none of them is, yeah. So the point is, it means that if a star takes 10 to the power 10 years to evolve, it's a very good approximation during that time.
Okay.
That is what is meant. I mean, because, astrophysically, everything takes a very long time to evolve.
Yes, sir.
Okay. Right. So now let us take examples. Let us take the case of n equal to 2. What is the n equal to 2 case? What is this? It is the case of a simple harmonic oscillator. And so, virial theorem states that 2 Ke is equal to 2 Pe, which means the Ke is equal to Pe. So if you have, when you study crystals, for example, and there is a statistical sample, then if suppose you have interaction between the atoms is like a simple harmonic oscillator, okay, potential, quadratic potential, then you talk about equipartition of energy, and this is where it comes. That is, there is an equal amount of energy in kinetic and potential energy. You get the point?
Yes, sir.
Okay, so this is like this is an example of an Virial theorem in operation. But what is of our interest is that of astrophysics, where I require n equal to -1. Now, what happens in this case? What happens in this case is that twice the kinetic energy is equal to minus the potential energy. Okay? And this has some very interesting applications. Okay? For example, um, now the kinetic energy can be deduced from velocity profile, which in turn can be done by Doppler. So, kinetic energy can be measured or estimated. Now, if there is a system which is in a kind of an equilibrium that is not evolving very fast, suppose there is a spherical system, then the potential energy is roughly equal to minus gm square by r. Okay. Hence, Virial theorem states that twice the kinetic energy is equal to minus gm square by r. If r is measured, that is the size of the thing, m can be estimated. And most of the time when they talk about the mass of the cluster of galaxies or mass of the cluster of star, etc., this is the way they estimate it. From Doppler, they find out the total kinetic energy of the system, random kinetic energy. From the telescope, with telescope, they can measure the size of the system. And using this and assuming it is virialized, you estimate the mass of the cluster of stars. Is this clear? So this is an astrophysical application. Okay, I'll give some problems here also. Is it okay?
Okay.
Okay. Now, lastly, I will come to um,
Yes, sir.
lastly, I will come to application of virial theorem in birth of stars. Now, let us consider a spherical cloud of gas at some finite temperature. And let's assume that the pressure is slightly less than gravity. So what is the implication of that? The pressure is almost equal but slightly less. So if suppose you have an object and there is a force which is acting in this direction, another force which is acting in this direction, if F2 minus F1 is much less than F1, that is, the difference between the force is very less, then what happens? Yeah.
May repeat? I didn't process that.
So what will happen is it will move in the direction of larger force, but it will move very slowly because the difference is very small. Similarly, in this case, gravity is more, hence contraction. But difference between pressure and gravity is very small. Hence, contraction is very slow. Is that okay?
Yes, sir.
Now, if this has an important implication, you see, in thermodynamics, in thermodynamics, if gas expands slowly, we call it a quasi-static process, which implies although it is expanding, we assume that there is a near equilibrium at every stage. Is that okay? Anirudh, Divya,
Yes, sir.
Ashima, Kausalya. Okay. And so it is a quasi-equilibrium process. Okay. Similarly, slow contraction implies a quasi-virialized process. What does this imply? Virial theorem is assumed to be valid at every stage of contraction. Okay. Is that fine?
Yes, sir.
Okay. Now, suppose at t equal to t1 time, I have kinetic energy is equal to KE1 and potential energy is equal to PE1, which is equal to minus Gm square by R1. Okay, it is a radius. Then it contracts and at t equal to T2, Ke equal to Ke2 and PE2 is equal to minus Gm square by R2 square with R2 less than R1. Now, since Virial theorem is valid at every stage, we have two Ke1 is equal to minus Pe1 and 2 Ke2 is equal to minus Pe2. It implies twice the change. Okay, so twice delta of Ke is equal to twice Ke2 minus Ke1 is equal to minus Pe2 minus plus Pe1. And so this is equal to Gm square by 1 by R1 minus 1 by R2. Is that okay?
Yes, sir.
Okay. Now this del Ke is measure of temperature because it is a kinetic energy of the molecules in the cloud. And so, okay, so I have twice delta Ke is equal to okay, so delta Ke. Okay, and so since R2 is less than R1, one by R2 R2 is, if this is more, have I done a mistake somewhere? Yes, I have done a mistake somewhere. So let me put it this way. And what is PE? PE itself is negative. So I have minus of minus Gm square by R2 plus Gm square by R1, which is equal to G, same thing I get. Huh? Gm square into 1 by R2 minus 1 by R1. Okay. So since R2 is greater than R1, 1 by R2 is less than 1 by R1, implies that RHS is greater than 0. Sorry. So R2 is less than R1 because it is contracting. So 1 by R2 is greater than 1 by R1. So the RH is greater than 0, which implies delta KE is greater than 0, implies that temperature of gas increases. Is this clear?
Yes, sir.
Okay. And so this is how a cloud of gas contracts, temperature increases till a point is reached where fusion is initiated and then the contraction stops. So this is how Virial theorem is relevant for star formation. Is this clear?
Yeah, yes, sir.
So I will stop with this. Any questions?
So any reference book you can suggest for this?
It's a book called, okay. A simple book is by Frank Shu. What do you think? Oh, Mandy. Okay, so this is the book.
Okay.
Okay, yeah. Okay, yeah. I think we'll end it here. Thanks a lot.
Okay,
Yeah,
sir.
bye, bye.
Thank you. Thank you.
Thank you, sir.
Bye, bye.